Right. Good morning, everyone. We are now recording, and so we're ready to get started. Uh, what we're going to do today is we're going to get started with our discussion of permutations. Uh, the idea at this point is we've played with some puzzles, the swap puzzle particularly last week, and we uncovered a few observations. We uncovered some things like depending on the kinds of legal moves we're allowed to do, whether it was swap an arbitrary two boxes or swap only the contents with box one, or to pick any three boxes and cycle the contents around, depending on which legal moves we were allowed to do. We were able to solve certain arrangements or certain permutations of the objects in the boxes, and some we weren't able to solve. And so the real question is, why can we solve certain puzzles? Why can we not solve other ones? What are the reasons for why it's impossible to solve other ones? And what is an underlying mathematical framework that we can sort of put all of this stuff on top of and use mathematics to answer these questions? And the mathematics we're going to need is what's known as the theory of permutations. And so you may have seen permutations before. Permutations, as the definition says here, it's a permutation of a list of objects. It's just some rearrangement of these objects. So you may have used the word permutation as a synonym for rearrangement. In other words, they're meaning the same thing, rearrangement versus permutation. They're sort of just two words to define the same thing. We're going to take a different viewpoint, though. We're going to take a more sophisticated or mathematically sophisticated viewpoint, and that a permutation for us is not just going to be a rearrangement of objects, but a permutation is going to be an action that has been performed. And so we're not thinking of it as a static kind of fixed object rearrangement, but as something that has happened dynamically. Things are moving around. And it's with that viewpoint that there's some movement happening that we're able to develop a theory that's going to help us in understanding these puzzles. And the theory itself is useful in many other places as well. Permutations is sort of the foundation of group theory, which I alluded to on the first day, has applications to chemistry, physics, pretty much everywhere. Cryptography, internet security, all of these things have group theory at the heart of them. So let's get into some definitions here. Our preliminary definition, as I refer to it here, is just it's a rearrangement of objects in some set. So that's our preliminary definition. Oops, I seem to have lost my pen. So give me 1 second to get it back up and running. All right, now I'm good to go. So I'll have to bring hopefully it'll come back automatically. There we go. Perfect. We're up and running again. Okay. So let's just run with this preliminary definition of what a permutation is. So for example, I could have three objects, the numbers 1, 2, and 3. And we could do things like, well, let's rearrange them. So I can write them in the order 1, 2, and 3, or I could write them in the order of 1, 3, and 2, or 2, 1, and 3, or 2, 3, and 1, or 3, 1, and 2, or 3, 2, and 1. And I think we've got them all here, all possible ways to write the numbers 1, 2, and 3 in any possible order. And so these are all the permutations. Of the objects 1, 2, and 3. There are 6 permutations of those objects, assuming we've been able to write them all down. So there are 6 permutations, 6 arrangements of those objects. But as I said, we're going to be more interested in not so much these permutations as sort of static objects, like the 1, 2, 3 is a permutation. It's the things haven't been reordered in any way. 1, 3, 2, the second one there, is a permutation. But we're going to be more interested in, not 1, 3, 2 as a static object or a static arrangement, but as how it was obtained. What was the action performed on the original arrangement 1, 2, 3 that allowed us to produce that new arrangement? And so this would be where we'd think, well, the second and the third object had swapped positions. So that's where we're going with this, is we're going to start to think about permutations as actions that have happened. Okay, so maybe the next one. How many permutations are there of the objects in the set 1 to 8? How many permutations are there of objects in the set 1, 2, 3, all the way up to 8? All right. So maybe I'll pose this to all of you. How many permutations are there? You don't have to give me the numerical answer, but you can give me an answer that tells us how we can compute such a thing. Yeah, 8 factorial. So this is probably the extent of what you did with permutations in maybe high school or previous classes. You might not have looked at them as objects that you can do algebra with, but these were the kinds of counting questions that we had. How many permutations are there of these distinct objects? You may have also, if you did MATCOM 201, how many permutations are there of objects where you had objects that repeated? So those were more enumeration problems. So let's just jot down why we know this is the case. So what we can do is we can think of this as, a permutation as we've got our disks 1, 2, 3, 4, 5, 6, 7, and 8, and we want to place these disks into these locations 1, 2, 3, 4, 5, 6, 7, 8. And so there are 8 choices for a disk that we can put there. Once we put a disk there, there are 7 left that we can choose from, and any one of those 7 can be placed here. We got 6 choices for this spot, 5 choices, all the way down to maybe the second last one would be 2 choices, and 1 choice for the final one. And so there are 8 times 7 times 6 times ... times 2 times 1, or what's referred to as 8 factorial permutations. 8 factorial ways to arrange those objects. So if we're playing this game, there are 8 factorial possible ways to start the puzzle off. And then we'd have to go ahead and try to solve it. So in general, if we have n distinct objects, the number of permutations of those objects is n factorial. So let's look at the 15 puzzle board. How many ways can we take, can the tiles on the 15 puzzle board be arranged? So again, the tiles, we've got these 15 tiles, including, and then an empty space as well. And how many ways can we arrange the tiles on this board? If I was just to take all of these tiles and randomly place them on the board, how many ways can we do this? Any ideas? So again, well, maybe I should put these in boxes. Yeah, I've got some answers there of, looks like there's 16 factorial. So I've got all these tiles, and I want to place them on the board. There's 15 tiles, and then what I often refer to as the empty space. So we've got 16, and I'll put in quote, tiles that we're going to arrange on the board, because one of them is the empty space, so it's not really a tile. And so there's 16 factorial ways to arrange them. 16 factorial ways to arrange the tiles. As a follow-up question, how many ways can we arrange the tiles if the empty space is to be in box 16? So I want to distribute all the tiles onto the board, but I want to make sure that the empty tile is in the last spot. Yeah, exactly. There's going to be 15 factorial in this case. There's 15 factorial. The empty space is now in box 16, so you've now got 15 tiles left to distribute into 15 spots. So there's 15 factorial ways to do that. It turns out that these numbers are going to have some significance for us when we're looking at solvability of the 15 puzzle. And we'll see to that once we get into chapter 9 is where we really investigate the 15 puzzle, once we've laid down the foundations of all the permutation theory. Okay, so far we've just been talking about how many of something. So how many ways are there to arrange tiles in boxes? How many ways are there to permute objects? Now I want to go to our mathematical definition of a permutation. The mathematical definition is what starts to get us in this direction of a permutation is we can think of as an action, and then we can start doing things like, what if I did a permutation followed by another permutation followed by another permutation? So I can start having them act on each other. And that's going to turn out to be a viewpoint that is quite helpful when developing this theory. So the formal definition, or the mathematical definition of a permutation, is that a permutation of a set A is a function which takes as input the elements of the set and gives as output the elements of the set and is bijective. So it's both one-to-one and onto. So in terms of how this connects up with what we have before, let's say I was to lay the tiles out here. I put 7, 3, 2, 1, 5, 4, 6, let's say 8, something like that. So I laid the tiles all out. How am I thinking about this as a function? Well, I could think of it in this way. I could think of how the puzzle started in its solved state and where the pieces now are. So tile 1 has gone to box 4. So 1 has gone to 4. Tile 2 has gone to box 3. So 2 is the input and 3 is the output. So this is how I can maybe start to think about this as a function that represents how things were arranged. We'll get much further into that in a later section where we really connect permutations with these puzzles. But for right now, that's just sort of an indication as to why or how we're going to think about these permutations as functions. So this is the more rigorous way to think about a permutation. Think of it as a function. It's got some inputs and some outputs. Inputs are usually the objects, and the outputs are their positions where that object now resides. So a couple of things just as a refresher. So we built it on the idea of a function and this notion of being bijective. So I just want a quick function refresher so we're all on the same page here. What is a function? A function from a set A to a set B is a rule that associates to each element of the input set, or the domain A. It ties it or associates it with exactly one element of the output set, or the set, what we call the codomain. What does the term bijective mean? Well, bijective refers to two things, one-to-one and onto, or injective and surjective. So a function from A to B is one-to-one or injective if no two elements have the same image, and it's onto if every element in the output space has been hit by something in the input space, and something that's both one-to-one and onto, or injective and surjective, is called bijective. So that's just a bit of terminology. I'm not going to harp on it too much because these kinds of things are just going to be natural in what we're doing. So let's go ahead and focus on what a permutation is for us. So a permutation is a function now. So we're going to be mostly focused on permutations of the set of elements 1 to n, which we've denoted that set by square bracket n and then closing square bracket for various values of n. And so now we want to think about, okay, how can we represent a permutation? So this is where we're going to start to deviate from how you normally think about functions. If you're thinking about functions because you're coming from things like courses like calculus or linear algebra, functions for you, maybe there's an input variable and a formula that's giving you the output variable. You know, like a function in calculus could be like f of x equals x squared. So x is the input and the squaring, x squared, is the output. So there's always a formula associated with it. That's not going to be the case for us. All our functions are going to take as inputs some numbers 1 to n and will output 1 to n. So we have to think about how can we represent these things. We're not going to be representing them as sort of these analytic graphs or these graphs like parabolas, etc., that you may be used to thinking about. We're not going to represent them as formulas involving some variables. The way we're going to represent our functions is well, there's a few different ways. So I'll go through a couple of them now. So let's say we've got a function alpha. Its input set is the set of numbers 1 to 3, so 1, 2, and 3. Its output is going to be that same set of numbers, 1, 2, and 3. So 3 objects are in the input set and 3 objects are in the output set. And so how can I define that? Well, the inputs are 1, 2, and 3. So those are our possible inputs into our function. So I just need to list what the corresponding outputs are. And so this is how we can define our function. Alpha 1 goes to 3, alpha 2 goes to 1, and alpha 3 goes to 2. So that's how we can define our functions. Okay? Because our sets are finite, we can just exhaustively list how all the inputs get mapped to the outputs. In calculus, for example, if you want to think about functions there, the sets that you work on are infinite, like the set of all real numbers. So you can't just explicitly list the input values and the corresponding output values. That's where those formulas come in, that they tell you how the inputs go to the outputs. But for here, our sets are finite, so we'll just list them. So I can consider another one, b. Let's say b is a function that takes the set 1 through 5, maps it to itself. And so then what I need to do is I just need to say where each of the inputs goes. Now, when I'm writing down my function in this way, I have to realize that what I'm doing is I'm producing a permutation. So permutations are, as I said, bijective or 1 to 1 and onto. What does that mean? That means that all 5 numbers must appear as outputs. So if we think about it in terms of distributing tiles on the swap board, so if I'm back here, I'm never putting 2 tiles in the same box. All the tiles have to go to their own box. And so that's really where this 1 to 1 and onto-ness is sort of coming into play. So where can 1 go? Well, let's just write down an arbitrary example here. So maybe 1 goes to 1. That's fine. It can go to itself. Maybe 2 goes to 2 and 3 goes to 3. Sure, they all go to themselves. The outputs 4 and 5 still have to appear, because I can't say that 4 goes to 1 because I already have that 1 goes to 1. So I'm going to have all values appearing as the outputs. That's the bijective nature in the definition. So that's just how we can think about it sort of from an intuitive perspective. I need the numbers to appear. So for example, maybe 4 has an output of 5, and 5, when it goes in, the output is 4. And so there's our permutation. Now that's one way we can describe a permutation, is just by explicit listing of all the values, their inputs and their outputs. Turns out that there's still a lot of writing that goes on there, and it's, in some sense, there's extra writing. I can be a little bit more condensed in how I write these things. So the way I could do this is I could write it in what we call array form. So in array form, what I do is I just write down an array, or a matrix of 2 rows, think of it that way, where the first row consists of all the input values, 1, 2, and 3, and the second row consists of the corresponding output values, so alpha of 1, alpha of 2, and alpha of 3. So in this case, our array would be 1, 2, and 3 is our first row, the inputs, and 3, 1, 2 is our second row, or the corresponding outputs for those inputs. And we get all the same information then. We know that 1 goes to 3, 2 goes to 1, 3 goes to 2, just by reading the entry in the top row and then the corresponding entry right below it. So for beta, 1, 2, 3, 4, 5 is our inputs. Our outputs would be the corresponding beta values. And those values are 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 5, and 5 goes to 4. So that's our array form. That's what I've written over here. That's our array form description of a permutation. These are the kinds of objects that we will be dealing with for the entire term. These are our fundamental objects, permutations, which are functions that are bijective. And so the bijective nature just means that on that second row in the output row, all the numbers have to appear rearranged. So that's where this sort of permutation comes in. The second row is a permutation of the top row, where I'm using the permutation in our informal way as just an arrangement of objects. Sometimes it helps to have a visual representation of these things in terms of an arrow. And so this would be our, quote unquote, our graph representation of the permutation of the function. So here, 1 in our input, it gets mapped to, or alpha of 1 is 3. So 1 goes to 3. So we put a little arrow indicating where it goes to. Our function takes 2 as an input, and it outputs 1. So 2 goes to 1. And 3 goes to 2. So we draw that in like that. So that's what's known as our arrow form. It's our arrow form of our permutation. And so for the beta one, we get these. 1 goes to 1, 2 goes to 2, 3 goes to 3, and 4 and 5 switch. The nice thing about the arrow form is it sort of shows you what the action is, like what's happening. The permutation, as I said, we want to think of an action, something being done, and it shows you what's being done. It shows here how things are moving, especially with beta. Beta, it's very clear from the arrow form now that what it's doing is it's swapping the contents of 4 and 5 in some sense. If we think of this as sort of the swap puzzle, it's switching two things. Whereas alpha, what it's done is it's cycled things around. It's done sort of what we call a 3 cycle when we were talking about moves on the puzzle from last week. We're going to talk about cycle arrow form and cycle form in chapter 4. That turns out to be a more condensed version of these representations, which contains all the same information, but actually is much, much more powerful. And I'm going to delay it till chapter 4 because we don't really need it as of yet to explore what permutations are. But we'll see that it's a condensed form that contains all the same information, and yet we can do a lot more with it. So let's go ahead and look at some examples. So the identity, or do-nothing permutation, it's denoted by this fancy E, sort of loopy E, or a fancy epsilon, if you want to think of sort of the Greek letter. And what it does is it just maps every element to itself. So if I look at 1, 2, 3, up to n as my inputs, then all the identity does is just map them all to themselves. So that's what the identity permutation is. An n cycle is a permutation that cyclically permutes n values. So if again we write down our n values, then in this case we could be that, well, I've sort of drawn a picture down below in terms of the arrow diagram to sort of capture this, but to cyclically permute, there's really a couple of different directions we could permute these. So for this one, we're just going to say that 1 goes to n, and then 2 goes to 1, 3 goes to 2, and so on, and n goes to n minus 1. So the picture's down there below in that 1 sort of shifts off all the way to the right, and everything else sort of drops back by 1. So this is what we call an n cycle. Now here is why we want to think about permutations as actions, why we're thinking about them in terms of their function form. This is really the key step in why everything works moving forward. The idea is, till now, if you've been dealing with permutations as just arrangements of objects, then, oh, did I write down the wrong thing? Oh, 3 should be 2. Thank you. Yes. 3 goes to 2. Thanks for that. Thanks for catching that. So what we're going to do is, if you are, so as I said, if you were thinking about permutations as just arrangements of objects, sort of these static things, you know, a permutation is an arrangement of objects. So here my books on my bookshelf are arranged in a permutation. That's all well and good, but we're interested in combining permutations with each other. And so this is this idea of composition. And so since permutations for us are functions, we can just do regular function composition. So for example, if alpha and beta are 2 permutations on 5 objects, alpha is given there. It sends 1, so 1 goes to 5, 2 goes to 3, 3 goes to 1, etc. And beta does whatever it does there. 1 goes to 5, 2 goes to 3, and so on. Then what we can do is we can compose them together. We can follow one permutation by another. And so the way I'm going to do this is just by stacking them up in terms of their arrow diagrams. So let's draw one. Alpha, 1 goes to 5, 2 goes to 3, 3 goes to 1, 4 goes to 4, and 5 goes to 2. So there's our arrow diagram for alpha. If I do the same arrow diagram for beta, or the arrow diagram corresponding to beta, so 1 goes to 5, 2 goes to 3, 3 goes to 2, 4 goes to 1, and 5 goes to 4. Then what I can do is I can read this diagram as starting with the number in the very top and finishing with the number in the very bottom. I can make a new permutation. And that's going to be the composition of alpha with beta. So first do alpha and then follow it with beta. So this one has alpha goes, we just read the diagram through. So alpha takes 1 to 5, and then following it with beta, beta takes 5 to 4. So what happens in the end is 1 goes to 4. And then we just do that for the rest. 2 goes to 3, and then to 2. So 2 will end up just landing back at itself. 3 goes to 1, which then ends up going to 5. So 3 goes to 5. 4 goes to 4, which goes to 1. So 4 goes to 1. And at this point, we already can see from the diagram what 5 has to go to. 5 has to go to 3 because it's a permutation, so all the numbers in the output have to get used. No No two arrows can point to the same output. So 5's got to go to 3, but let's just double check to make sure we get that in the diagram on the left. So 5 goes to 2 from alpha, and then 2 goes to 3 from beta, so 5 goes to 3. And so there's our, what we call the composition of alpha and beta. We also refer to it as the product of alpha and beta. I will refer to that as we start to move throughout this course, as a product or multiplication, because it turns out that we can start to think about these things as ways to do algebra on permutations. Okay, so we've now got a way to combine two permutations. Now, this is not something that we thought about before when dealing with permutations in, say, high school or in MATCOM 201, if you've done that. Permutations were just arrangements. Now we're thinking of them as having sort of an action associated with them. So we're able to combine two of them together. So doing alpha first followed by beta gives us a new permutation. Now, this gives us our new permutation alpha beta, which is the function obtained by first applying alpha and then applying beta. We've done it in the arrow form above, but we can also do this straight from the array form as well. We just got to think about how we're going to do this. Doing it from the array form is actually going to be how we're going to do it in practice. We're not going to draw these arrow diagrams for permutations just in order to do multiplication. We're going to have to work with them in the array form to save ourselves from all the drawing. But the arrow form helps us visualize what's going on in terms of how we constructed the product. The array form is how we'll work with it notationally. So how is this product going to be done? Well, what I do is I start with a particular number, let's say 1, and I think about what is happening. Well, 1 is going to go to 5. So 1 goes to 5. That's what alpha does first. And then out of alpha comes this number 5. So then I go into beta and I figure out where 5 is. And then I see what comes out of it. And what comes out of it is the number 4. So I trace this through. I say, okay, if 1 goes in, alpha goes 1 to 5, and then beta takes 5 to 4. So 1 goes to 4. And I want you to just go through the remaining 4 numbers and see what 2, 3, 4, and 5 have to go to in terms of this, tracing it out. For your question in the chat, Jane, can you cyclically permute the other way? Absolutely. An n cycle really just refers to the fact that n objects are sort of being permuted around. So I gave one example of an n cycle, but you can go the opposite direction. Yeah, there are many examples of n cycles. So feel free to work out the next values. So 2 goes to 2. Yeah, that looks good. So we'll follow it through. 2 goes to 3. 3 goes to 2. And so 2 comes out. And then similarly, 3 goes to 1. 1 goes to 5. So 3 goes to 5. Now, if you listen to what I'm saying as I do this, this is the kind of thing you want to be saying to yourself as well. You'll be doing this all course when we're multiplying permutations. So the next one, 3 goes to 1. 1 goes, oh, sorry, that's the one we just did. 3 goes to 1, 1 goes to 5. The next one, 4 goes to 4. And then for beta, 4 goes to 1. So 4 goes to 1. And again, the way is we start with 4. It goes to 4. 4 comes out. I figure out where it is over here. There it is. And out comes a 1 in the end. And then 5 goes to 2, and 2 goes to 3. So 5 goes to 3. So there's our result. And if we compare it with the arrow diagram up above, we see that we get the same result. Now we're moving from left to right when we do this. We read our compositions from left to right. And so this is our definition then for how we are computing the product of two permutations. We call the composition or the product. So if I have two permutations, alpha and beta, I can form their product, alpha beta, by doing the following. I start with any particular value for the input k, and I see where it goes to under alpha, that's alpha of k, and then where does it go under beta, that's beta of alpha of k. So what this means is that alpha beta of k, so the product permutation, if k is a particular input, how do I work out what the output is for k? I first have to find out what alpha does to it. Whatever that number is, I then plug that into beta and work it out. That's it. That's what we've done up above. So for example, if I wanted to know what 3 goes to in my alpha beta up at the very top there, I first go, what does alpha do to 3? It takes it to 1. So 1 comes out. And then I look at, what does beta do to 1? So what does beta do to 1? What does beta do to alpha of 3, in other words? So here's the important point to keep in mind. Composition for us is being done from left to right, which is opposite what you would have done in, for example, calculus or linear algebra. Their function composition is you would start with the function on the right and compose from right to left. So I will just say that here. In calculus, if we wrote fg of x, then that would have been, you would have done g of x first, and then you would have followed it by f of x. But that's not what we're doing in this course. So calculus would have done this composition in this way. The way we're doing our composition is we're doing it from left to right, alpha first and then beta. And you may say, why would I do this? Why would I mess with a convention that you're so used to? The reason is if I said to you, for example, take your Rubik's Cube. You got your Rubik's Cube, and I want you to do an R move, so move the right face, the up face, the down face, and then do a left inverse move. It's all right if you don't know what these are. It's just really, R is just saying turn the right face 1 click in the clockwise direction, and sort of continue on there. Well, the way you would read this is you would read it as first do R, then do U, then do D, then do L inverse, because we naturally read from left to right. And so that's why we're taking our convention to be left to right composition, because that's how we are naturally going to read these move sequences. These are actions that are happening. So alpha is an action, beta is an action, and so we read the order in which actions are happening from left to right. So that's why we are doing our compositions from left to right. It turns out that if we did them from right to left, like calculus, things would get awfully confusing, and we'd have troubles trying to figure out what to do first versus what to do second. Whereas if we just think about these things, this whole course built around the idea of doing puzzle moves, and we read puzzle moves from left to right, so that's how we're going to do our permutation compositions. And this is a natural way to do permutation compositions. It's how permutation composition is encoded in Sage Math. So it's done in this way, left to right. So everything's going to be consistent in this course in that way. So let's look at some examples. So we've got alpha, beta, and gamma. And they're given there in their array form, and we want to compute some products. So let's go ahead and work out some products. So the grouping parentheses tell us what products we want to do first. So for example, we'll write down what alpha is. And then I've got my grouping brackets, my beta, and my gamma are written here. And my grouping brackets are telling me which products I'm going to do first. Composition is only defined for two permutations. We can only combine two of them. But then once we combine two of them, then you can do a multiplication with another permutation. So the idea here is that if I'm going to write down the product of three permutations, I'm going to specify which ones to multiply first. So we're going to do the multiplication of the second two first. So let's do that. So this is going to be 1, 2, 3, 4, 5. And we apply that same mantra that we've had before. When I'm going to do the product, I'm going to start with 1. And I'm going to go 1 goes to 5, and then 5 goes to 4. So I end up with 4. Again, I'll just indicate for one of them. I go 1 goes to 5, and then 5 goes to 4. So 4 comes out. And I just do that for all 5 of those numbers. 2 goes to 3, which then goes to 1. 3 goes to 4, which then goes to 2. 4 goes to 1, which then goes to 3. 5 goes to 2, which then goes to 5. So this is computing products. This is computing products of permutations. And this is something we're going to do quite extensively over the course of the term. Now I'm going to work out the last one as well. 1 goes to 3, which then goes to 2. 2 goes to 4, which then goes to 3. 3 goes to 1, which then goes to 4. 4 goes to 5, which then goes to 5. And 5 goes to 2, which then goes to 1. And so there's our resulting permutation, the product of doing those three. So if I had a puzzle that I was working on and I did an alpha permutation to it, so move the contents from box 1 to box 3, the content from box 2 to box 4, the contents from box 3 to box 1, and so on. I did that alpha permutation. Then I followed with a beta permutation. Then I followed with a gamma permutation. The product of doing all three of those things would have been equivalent to just doing this one permutation here. Now what I'm going to do is I'm going to do the same product of three, but I'm going to switch the grouping brackets. So instead of doing the beta gamma one first, I'm going to do the alpha gamma product first. So let's just jot down what this product is. So that's that one, and then 1, 2, 3, 4, 5. And so that's 3, 4, 1, 5, 2, and 5, 3, 4, 1, 2. And then the gamma is 1, 2, 3, 4, 5, 3, 5, 1, 2, 4. So that means we're going to have to do the product of alpha beta first and then follow it by a product with gamma. So take a moment just to work on the product yourself. And if you finish it, then you can just return in the chat. You can just return the list of numbers as they would appear in that second row, just to make it easy to communicate that information. So go ahead and work out this product and then write down the list of numbers. See a 2, 3, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1. Yeah, it looks like a 2, 3, 4, 5, 1. And do you notice anything with the previous calculation? Yeah, it's the one we just did before. These two end up being equal. So what does that even mean? That means if I'm going to multiply three permutations, alpha, beta, and gamma, in that order, so alpha, beta, gamma, I'm going to have to multiply two of them first before I multiply by the third. This tells me that it doesn't matter whether I multiply the first two first or the last two first. Either way, I'm going to get the same answer. So in general, these grouping brackets of which one to do first doesn't make any difference. So we call that the associative property of permutation composition. And it means that we can unambiguously write alpha, beta, gamma, without having to specify which two to multiply first, because we could multiply alpha, beta, or beta, gamma, and it doesn't matter. In fact, you might be able to see why if I do this. If 1 is my starting number, then 1 goes to 3, 3 goes to 4, and 4 goes to 2. So 1 in must have 2 come out. And so there's our 2. So we just play this sort of snaking game along all these permutations. However many I'm multiplying together, I just snake through them in this way. What does the first permutation take? 1, 2. Whatever comes out of it, I put into the second one. Whatever comes out, I put into the third one, and so on all the way down the line. And then I can do the same thing with 2. I can read it across right now. I can go, so I'm looking at that line, this line here, and I say 2 goes to 4, 4 goes to 1, 1 goes to 3. So 2 ultimately goes to 3, just by reading permutations across. And so, for example, if I make the connection with the cube, I can write things like R, U, L inverse, U, R, D without having to specify grouping brackets. You know, how each move corresponds to a permutation and tell you that you need to multiply these ones first before those ones. This tells me immediately that I don't need grouping brackets. I can just read from left to right, and I will get the result, and it's unambiguous. So let's look at another example, alpha, gamma. So here, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. See if I can copy down alpha from above. 3, 4, 1, 5, 2 was alpha, and gamma is 3, 5, 1, 2, 4. So go ahead and compute that product and let me know what you get for the last line of it. Yeah, looks like some of you getting it. 1 goes to 3, 3 goes to 1, so 1 goes to 1. 2 goes to 4, which goes to 2, so 2 goes to 2. 3 goes to 1, which goes to 3, so 3 goes to 3. 4 goes to 5, 5 goes to 4, so 4 goes to 4, and 5 goes to 5. In other words, we get the identity. So alpha followed by gamma is the identity. Just to answer the question in the chat, is L inverse the same as R? No. So let me see. This is my right hand here, so it's on your left side, which is rather confusing. But this is my right hand holding the pen. An R move is a twist of the right face in the clockwise position, whereas an L inverse move is a twist of the left face in the counterclockwise position. So they're two different faces, the right face versus the left face, and the inverse tells you direction. Okay, so that told us that alpha gamma is the identity. So we would, we would say things like gamma is the inverse of alpha. Because if I was to do an alpha move, so start with a solve state puzzle, let's say, do an alpha permutation on it, and then do a gamma permutation on it, I get back to the solve state. So gamma effectively just undid whatever alpha did. So they are inverses to each other. Something else we can do with these is we can power them up. So we can take alpha and multiply it to itself. If I multiply it to itself n times, I call that the power alpha to the n. So for example, I could do alpha squared. So 1, 5, 2, and 1, 2, 3, 4, 5, 3, 4, 1, 5, 2. And I could work out what it is. 1 goes to 3, which goes to 1. 2 goes to 4, which goes to 5. 5 goes to 2, which goes to 4. 4 goes to 5, which goes to 2. 5 goes to 2, which goes to, sorry, this is where I must have made a mistake because I was going to get 2 again, so I have to check these things. 4 goes to 5, which goes to 2. 5 goes to 2, which goes to 4, so I got a 3 goes to 4, which is probably wrong. 3 goes to 1, and 1 goes to 3. So this is going to be my problem one here. So it's got to be bijective. All the numbers have to appear in the second row. So if you get them duplicating up, it means you made a mistake. So I'm going to recheck that 3. 3 goes to 1, 1 goes to 3. So 3 goes to 3. 5 goes to 2, which then goes to 4. So there is our alpha squared permutation. And we can do that alpha cubed, alpha to the 4th. What we do is we just keep multiplying these permutations to themselves. The key thing I want to just point out here is that I don't have to write down alpha times alpha times alpha. I already worked out alpha squared, so I could just write it as my previous permutation, alpha squared. 1, 2, 3, 4, 5, 1, 5, 3, 2, 4, and multiply that to alpha. 1, 2, 3, 4, 5, 3, 4, 1, 5, 2, and work out what that value is. So 1 goes to 1, which goes to 3, 2 goes to 5, which goes to 2, 3 goes to 3, which goes to 1, 4 goes to 2, which goes to 4, 5 goes to 4, which goes to 5. And so there I get alpha cubed by just multiplying 2. And you can do the same thing, alpha cubed times alpha, to get the next one. And so I'll leave it to you. We'll wrap up today. I'll leave it to you to just work out the alpha to the 4, alpha to the 5, and alpha to the 6. And alpha to the 6 should simplify down to something very nice. Just to give you a heads up, if you continue on that, you should get the identity for alpha to the 6. So you can double check your work in that way. All right, so I'm going to stop the recording now.